So, yeah, I wanted to talk about covert channels. Are we? Oh, okay. Excuse me. I actually intended this to be kind of an educational talk, just to introduce people to the concept of covert channels. What I see in when I look at covert channel tools, there's a lot of prepackaged stuff out there, and I'll mention a couple of them in my talk. But I see a lot of stuff where we've got these tools that do one very specific thing, but they're not very flexible and they're easy to signature, right? I mean, if we're talking about reducing detectability, we want to reduce the capability to signature that or to be profiled by heuristics. So, I should probably mention, my name is Jennifer Allen. I am the Red Team Manager for Twin State. I've been in some tech jobs. I really love all things hacking. I started coding when I was little and just kind of went from there. I've got some certs. I am a ham radio dork. And that's it. So this talk, as I mentioned, it's going to be covert exfiltration of data, and I'm going to be talking about topics concerning successful exfiltration, so it's going to be kind of a broad overview for people who aren't very familiar with the concept, but also getting into some Scapy and Python. I will tell you, I am not a long-time Python coder. So I have a developer on my team, and I'll hand him a piece of code, and he'll just give me this remorseful look. I just want to warn you guys, this is pretty raw stuff. He also gives me a bad look when I use Python 2.7. So Python, I'm like, dude, it comes out of the package. It's ready to go. I'm trying to roll some code. Leave me alone. So, the stuff we're covering today, Scapy does actually work for Python 3. I wanted to make this simple so that people who aren't familiar with any of this can just jump into, say, a Kali Linux box and be ready to go and not have to worry about importing extra libraries. Yeah, so you can be, really good and do proper code and use Python 3, just so you know. So this talk assumes not very much experience. It helps if you understand network protocols, because I'm really going to be looking at, some packet captures and talking about the fields in protocols and stuff like that. So if you don't really understand that, you might get a little lost. Hopefully not too much, though. And the next level, like I was saying, this is really going to go into some basics, but I highly recommend you check out covert channels on like Out of Band, air-gapped media. There's some really amazing air-gapped covert channels out there these days. I mean, the things they can make a piece of hardware do that it was never designed to do, like, blows my mind. As well as things like covert timing channels, really subtle stuff, and detection algorithms. So if you want to make a covert channel, you really need to understand how you're going to get picked up, right? So this gentleman here could probably tell us all about that. And then all right. So the Python I'm using in the presentation, again, very rudimentary, but I did throw it up on a GitHub repository just so you can take a quick peek if you want to try it out, while I'm talking. So here's one way to do it. Okay, first of all, why are we hiding? There's a lot of reasons to hide, a lot of reasons to use covert channels. Usually when you say you're using a covert channel, you're either a spy or a bad guy. That's like the two assumptions there. But in reality, you may be an attacker, you may be stealing data. You may actually want to protect intellectual property or some form of data that you can't risk exposure of. You might be subverting security controls. You also might just be attempting to avoid attention. So if you're a person of interest and you want to protect your data or your communications, you may want to not only use encryption, but also reduce detectability. So how to hide? Again, encrypting data, that's a different talk, but there's really, these are the two components of hiding, right? You can either encrypt your data, or you can reduce the detection so people aren't even looking at it. And those are, when people look at communications, they look at those two realms, right? Detectability and decryptability, I guess you could say. So the signature-based detection is what we see in a lot of environments. A lot of the folks I work with, clients and individuals, this is really all that they're doing. They're doing signature-based detection via AV and AM. Maybe they've even got some log correlation in a SIM, something to that effect. You get into some of the bigger organizations, and you may also see some behavioral pattern detections, deviations. They're going to be looking at things on the hosts, accounts, processes, storage changes. They'll be looking at the network, so protocols and endpoints, how the network lives and breathes. And that's what I want you to be thinking about as I go through this talk, is not just saying, well, how can I shove this into a data packet, but understand why you're putting it into one packet versus another, and how the packet should behave, how they should look. Like the teenager who's trying to act normal when they've totally done something wrong, like like walking in the house like past curfew. It's cool, it's fine. I didn't do anything. It's totally fine. So the data types, quantity, as well as traffic. Peaks, user norms, there's a lot that we can identify just by seeing, Bob doesn't work from 2 a.m. to 3 a.m. Why is he browsing the web for this one website that doesn't actually exist? That's really weird. So, you're going to want to understand the environment that you're working in and make sure that you know what you're trying to hide from. So there's a lot of existing tools, as I mentioned. There are, covert channels are nothing new. They've been around for a very long time. There are a lot of existing apps that you can download. Some of the concepts in hiding data, steganography, for instance, hiding data within other media. So things like JSTAG, STAGHide, OpenPuff. There's a whole bunch of you've heard of these. A lot of ways to hide via steganography. Identifying entropy in a file that has been stegoed will give you away, though. So that's something that, if you have a really good heuristic system or signature-based detection, they may identify, whoa, that JPEG is really weird. If you look at these levels here on the least significant bit, something's going on, right? So. Yep. So the next thing that we would look at is prepackaged covert channels, things like iodine, p-tunnel, CCTT. You can Google these. There's lots more. I just grabbed a couple of them as examples. And these are all pre-built tools, so they have a pre-built designation. And the problem with that is that you can't really customize it. It's not as flexible. So what I want to talk about today is build tools where you can more flexibly and dynamically create covert channels, possibly switch communication mechanisms in transit. And there are tools out there for this. So Ettercap is one of them. Scapy is the one we're going to be looking at today. That's actually a Python library. So anyone who likes Python will be familiar with the command prompt in the interactive version. And there's a talk later today about a Python covert channel called Stuffer. So if you guys really are digging this concept, check those guys out. So first of all, covert channels, again, elephants, right? We see elephants. So, that's the obvious, right? This is us seeing, an HTTP packet on the network. Okay. We've got somebody trying to get a website. There's more data here than we really recognize when we initially identify it, though. Our brains are trained to look at a picture like this and pick out key gestalts, right? We're saying, whoa, there's two elephants, there's a baby elephant, they're doing something, they're interacting. We begin to relate to it, and we focus in on specific data within the image. So we see 3 elephants. There's another piece of data. If we were really drilling down, we'd say, whoa, that wasn't just elephants, that's 3 elephants. Furthermore, we can also identify that there's more data encoded in this picture. There's a juvenile and 2 adults. No tusks. So we can keep doing this. How many trunks are there? Anyone? How many tree trunks? So the point here is, when you look at a piece of data, understand that every single bit, every single aspect, we could look at all of the color values on this picture. We could look at quantities of items. We can look at a lot of information and use that to encode more info than would be immediately identified by the brain, the signature matching mechanism that is looking for specific data to quantify. So this is what we're really going to do when we get into covert channel development. We're going to start by looking at our average network, and we're going to understand pardon me. I knew that was going to get me. We're going to look at the pattern matching that the network brain is doing. So we're going to say, okay, this network has these characteristics. what are they looking for? You know, are they picking out the elephants? Are they picking out the trunks on the elephants? Where does that data recognition end, and where is the void, the black box, where I can put information that won't be noticed? So first of all, we really need to create a baseline. We can do this in a couple ways. So you can say, okay, well, I'm on an IP network. I can use public and research data, right? You can go out there and you can find a lot of information about statistics on an average IP network or any other public protocol that you land in. You can also analyze existing signature sets. So this is a great way of, you know, hitting the masses. If you want to go into a network and get 9 out of 10, go and look at the signature sets for products that are designed to catch bad activity, right? I mean, that's a really easy way of finding those empty spaces within the data. Even better yet, though, is to monitor in the target network and actually start to do a baseline yourself. Start to understand the enemy, so to speak, or the network that you're attempting to breach, or rather move through quietly. So when you think about a network, understand there are so many different ways of detection. You know, we've got IDS and IPS, firewall, SIM, AVAM, maybe even a user notices something off, right? So if you start throwing packets into an environment and some device catches it and it's like, I don't know what's going on, there's something happening here, we're getting all these packets, we don't want them. A user may call out. NAC, HIDS, all sorts of different host and network-based platforms will catch unexpected behavior. So what we really want to do is identify on the network the largest amount of traffic, right? We're going to look for the level of detectability in the environment. So we see a lot of Ethernet on an average network. We're probably going to see a lot of ARP. We're definitely going to see a lot of IP protocol. I mean, most everything on layer 3 you're going to see is IP. Then we'll start to see a divergence. And what I find is that the network admins and network engineers who understand network protocols will know to look for UDP, right? They'll know. However, unfortunately, a lot of folks don't even, it's like not even on their radar, right? So a lot of hacking tools out there attack using UDP as a transit medium. TCP is definitely above board. That's going to be noticed. A lot of TCP you're going to see recognized. HTTP, web filtering. I mean, even web filtering, that's like the basic stuff, you know? So if you're throwing stuff in and you're trying to reach a website that's a known CNC, you're going to be throwing up alarms everywhere. DNS, sometimes this is less detected, sometimes it's not. So it depends on the network you're in, right? So if you've got a network that understands that botnets love to use DNS as a CNC mechanism, they might actually be watching that and be signaturing a lot of DNS traffic that, excuse me, doesn't look normal. The CDP, so Cisco Discovery Protocol, for instance, little protocol you might catch out there. ICMP v6. Oh, the v6 protocols are great. A lot of people don't think about those. You know, they're like, nah, who's using IPv6? Nobody, except all the devices secretly behind your backs. So, those are a good one. And then a lot of protocols that we don't even think about, right? SSDP. I'm going to have you hold your questions to the end. Yep, thank you. So SSDP, and I'll talk about this one in a little bit. This is a really interesting HTTP over UDP protocol that you'll see a lot of from like smart TVs, and it's actually a service discovery protocol. RRCP, which is the Realtek Remote Control Protocol. I caught some of that in a packet capture the other day. Yeah, some custom apps, some really fascinating stuff out there. So there's a lot of protocols that you may catch in the living environment that you won't see in public data or in research papers. And this is why it's worth understanding the network that you're actually profiling and that you're going to be using covert channels in. So that all sounds easy, right? Like, how do we do that? So we start by understanding the common protocols. So protocols transmitted too frequently for cheap inspection. So this means we're going to be cutting down the likelihood, and everything that we look at, every consideration we take is just going to be helping us reduce detection a little bit more. So identifying protocols that are either too frequent for very basic. Now this is really the very simplest of detection. So cheap inspection, HTTP, ARP, DNS, if you have those really cheap firewall devices that are doing like some tiny bits of IDS and that's it, and they're matching like 5 vulnerabilities that happened 10 years ago. So you might get past something like that. Payloads that occur regularly on the target network. So a lot of times we'll see, as I mentioned, the DNS resolution. So if you're seeing resolution for an Amazon AWS site, oh, it's fine. It's in the cloud. It's Amazon. It's safe, right? I mean, nobody would ever put up a bad Amazon host. Okay. So, as well as unpredictable and obscure protocols that are too obfuscated or unfamiliar for easy fingerprinting and signature development. I caught, some OX8899, which is the RRCP protocol. And I was like, what is that? I spent a little while tracking it down. It actually is it's a layer 2 protocol from a switch. It's like pretending to be a managed switch. It's actually a dumb switch, but it uses this protocol and you can actually get it to do some rudimentary management over the network. And it broadcasts by default unless you set a pin. So it was just like one of those weird, ad hoc kind of things that I would not have seen on an average network. You might see payloads from high-level sources like userland and vendor-centric protocols. The Batman protocol is an open source wireless mesh protocol I caught one day out in the, I shouldn't say ether, out in the air, on the airwaves. Payloads that are highly dynamic and thus harder to profile. So the SSDP protocol we're going to look at is text-based, and it's very vendor-centric. So it's easy to kind of put stuff in there that's really hard to signature. Okay, so let's take a look. I'm going to switch gears on you a little bit, and we'll take a look at Scapy and Python, Scapy. So, first of all, the Scapy basics, constructing packets in Scapy is pretty straightforward. It uses a concept of layers for protocols. So we're looking at fields that build into layers that build into full packets. So you'll see I've got just a snippet of code here. I'm building a packet, and I'm identifying at the base layer the IP layer. All I'm telling it is a destination IP address of the loopback. And that's all I have to do. Scapy will intelligently populate defaults into the packet that we're constructing in each layer if it's not identified. The next layer up, and you can see the syntax is really straightforward, is TCP, Transmission Control Protocol. We've got a destination port of 25, and I'm not specifying anything there. So it's going to use its defaults for the TCP layer as well. And Scapy is really intelligent about constructing packets layer by layer based on the protocol that you're specifying. Now, you can build some really mangled packets in Scapy. So if you throw a packet out there and you put some crazy parameters, it's going to try to toss it on the network. And you'll open up Wireshark or start TCP dump, and it'll just be like, I don't know. This is like, here's a hex dump. Just have that. I have no idea what this protocol is. This packet. But usually you can intelligently build these if you understand at a basic level how the protocols stack and how to construct them. There's really easy syntax in Scapy as well. So packet.show is going to show us the full construction of the packet, and we'll see those in just a little bit. Packet TCP is just going to narrow in on the TCP layer. And then send packet, it's that easy. That's it. I just built a TCP packet going to port 25 and threw it on the network. That's all it takes. So Scapy is a really, really flexible library. Sending and receiving is pretty straightforward, and we can also send and receive expecting a packet negotiation to come back. Scapy has a lot of default protocols built in so that if you, say, send an ICMP, you send an echo request, and you get an echo reply, it's going to intelligently recognize that was the response. We can identify that the count that we want to send out is 10. And we can also apply filters as well. So we can say, well, I only want any destined to port 8080. And I'll talk a little bit more about those as we get into the code. So sniffing and handling, Scapy does a good job with this as well. We can, in this case, I'm building out a packet. I'm preparing to sniff the packet that I've constructed on the first line, and then I'm defining a way to handle that packet. So def do underscore this packet. I'm just going to print it out in this case, but we'll see some more complex functions in just a bit. And then I'm looping on the sniffing function, and every time I receive, so you've got sniff, every time I receive a packet, I'm going to say, okay, I'm only receiving a single packet, and then I want to do the functionality in do underscore this, and I'm only doing this to packets that match the filter TCP and port 80 or port 8080. The cool thing about Scapy is you can use both a Berkeley packet filter format, or you can use a Python function, so you can use Lambda functions, which is really, really neat. And the protocol layers are really easy to identify. So if you want to see what's in Scapy, all you got to do is go to a prompt where the Scapy library has been imported. Type Scapy. It'll come up with the arrows, just like you would see in Python. And you can type ls, and it'll actually give you a list of every protocol that is natively built into your version of Scapy. So it's a really, really straightforward environment. You can see more information about a particular protocol. So let's say I want to build ICMP. I can just type ls ICMP, and it'll give me the information on the fields. I can also look at sublayers. So if I'm building a DNS packet, and we're going to do that in just a little bit. If I'm building a DNS packet, I can look at the query response section solely, which is going to help us when we start to build the command and control that we're going to be doing in just a bit. One call out, if you're not familiar with the environment, help and ls are definitely your friends. Do check those out, because you can almost always get information, and it has very full documentation online. Okay, so let's get to the covert channel piece. So a few scenarios that I want to talk about, and I'm really going to focus on the firewall and an out-of-band or IoT channel, but we have a lot of situations that we can use to our advantage. So first of all, we've got our compromised host, the sad face on the left, and then we've got Eve on the right, waiting for the covert, either a full covert channel or maybe exfiltration of data. And typically we would be going through a firewall, right? So that's the least desirable situation, because that's where a lot of egress is going to be, analysis is going to be occurring, signature detection in the environment, in a lot of networks. So if we can avoid that, that would be ideal. One way to do this is mobile. If anyone manages a number of networks here, I'm sure you've seen those really annoying mobile devices pop up on the network, and your heart stops for a minute because you're like, oh my gosh, what's it loaded with? How many free apps did this person download? So you have a lot of BYOD in networks these days. You can also use to your advantage the wireless environment. A lot of organizations will have internal wireless as well as external wireless. The internal wireless is typically sitting right in the sweet spot in the internal network. Why not either you can crack the wireless, the typical attack surface there, or you can use it to your advantage in conjunction with an IoT device. And I'm going to invite anyone who's interested to visit the Hardware Hacking Village later today for another ESP8266 workshop, if you want to see an example of an IoT device that can provide this kind of firewall skirting technology. So the exfiltration through a firewall, we really want to identify the source and endpoints that we're working with, so we know exactly what path we have to traverse with our covert channel and what identification we're going to need to avoid. We need to determine the best protocol for the network and timeline that we have, and then create the covert channel according to the constraints. So let's put together what we've seen in Scapy. And I just want to show that we've seen enough that we can start to build right now. So we're going to have Bob, the compromised host, and Eve, the attacker, and we're going to build a two-way comm using just a few simple Scapy functions. Eve is going to be sending DNS command inbound. So this is, again, this may be detected by certain networks, and I'll show you how to get a little more tricky after this. But DNS commands into Bob, and then HTTP replies with the shell command standard output back to Eve. So this is really fast and easy, I promise. So we have Eve the attacker, and if you want to grab command.py, that's on the GitHub. First of all, we're going to encode the shell command into a DNS query. So to use Scapy, it's very simple. From scapy.all import star. And the command and IP address of Bob are going to be taken from the command line. As I warned you, it's very raw, dirty Python. I'm sorry. The next line here, enc command, you can't see my pointer, sorry guys, is going to just do some really basic encoding so that it's not really obvious that we're sending, cat Etsy shadow across the network in a DNS command. That's a little obvious. So we'll just use base64. At this point, this is not what I would consider a very good approach to this. Base64, we know that's easily reversible and pretty identifiable. Furthermore, when we see the DNS that it outputs, we're going to notice that there are capitals and lowercase letters. Now, I will say that if a user, say, does an NS lookup and types capitals and lowercase letters, that will actually get transmitted in the packet. Some applications retain the case and will just drop it on the network that way. So it's not unheard of to see that, but it's definitely something that if a person was looking at this, they may notice. So you may want to, come up with a more complex scheme to hide the command in the packet. But we're going to use base64 encoding, and we're going to, because base64 is padded, we're going to replace the equal when it's padding with a double equal sign with a .com, replace the equal with a .net, and if it's on the line, we're just going to put .org. And from here, we're going to also create a random transaction ID. And it's not fully random. We're going to do this so that it's a signal to Bob saying, hey, this is Eve speaking. You need to pay attention. So we're going to make the first 8 bits of the 16-bit transaction ID in a DNS request the all ones. So it'll be an FF. And then the second 8 bits are going to be randomized, so that it's not obvious that we're constantly sending FF00, FF00. That's not natural in a DNS environment. So now that we have our partially random transaction ID and our encoded DNS, we're going to send that to Bob. So you can see we've got Bob packet, and that's sending just an IP with a destination of Bob. Now, I would recommend in your environment you get a little more complex about how you're constructing your IP packets. You may want to identify a specific MAC address. You may want to use a source IP that's going to be trusted. You can change all of these in Scapy. The UDP we don't need to specify. Scapy will actually intelligently identify things like the destination port based on the upper protocols. So it will say this is DNS, so the default is going to be port 53. We're going to drop in our transaction ID, and then you can see I'm building a sublayer there of the DNS query and response, and I'm dropping my encoded command in there, and we're sending it to Bob. Next, Bob, the compromised host, has another short piece of code on it, receive.py. We are sniffing for DNS queries with our not quite random transaction ID. So you can see if you drop down to the bottom, while true, packet equals sniff, count equal 1, prn equal do underscore this, meaning if you catch a packet that matches the lambda filter, then do this function. And lambda x.hasLayer, and it's just looking for a DNS query specifically, and a DNS transaction ID that is greater than or equal to FF00. Pretty straightforward. Our ID is always going to land in that range, so we can just make short, easy code here for this example. Again, I recommend a more complex scheme, but this is an easy one to throw on the slide. So at this point, it's going to catch any packets from Eve with this special consideration. And at that point, it's going to grab the packet. You can see that I'm identifying in the PRN, the function, I'm identifying the packet inbound as in packet, and then I'm pulling out Eve's IP from the packet. So Eve can actually jump from one IP to another, and I don't have to let Bob know where Eve's residing, which is convenient if, say, I'm bouncing off of an IoT somewhere in the network, and I'm not always going to have the same IP address. At this point, I'm going to strip the command, replace the .com, .net, and .org with the correct base64 symbols, and then decode the base 64 to get the command, and I will drop it to a shell, grab the output, and actually run that. Oops, and I'm sorry, I missed a little bit here. So at that point, I'm going to send the standard output of the shell in an HTTP GET request as well. And I jumped ahead just a little bit. So we've got get string equal, and I'm actually building out a raw HTTP packet at this point that is going to simply create a get request for /index.php, AC equal, and this is just kind of like a typical format that you might see in any random web server log. Then I'm dropping the encoded string into, or the output of the command that we ran. I'm re-encoding it so that it's going to be just a big string, and you guys will see this in just a moment. It's going to be a big string of base 64. Looks like just a poor coding, you know, like some web designer did some poor coding. So now Eve is going to be sniffing for that, and I've actually extended command.py here. So you can see the added code below. I'm going to be looking for the HTTP, catch Bob's reply, and then parse the output. So I'll be decoding that base 64 string, and then I can see the results. So here is the sequence actually occurring. So we've got command.py, and I want to get an IF config readout from Bob. So I've identified Bob's IP address and the command I want to send. And you can see in the packet capture of Eve's packet outbound, the command packet, it is creating a DNS request. And you can see I'm looking for awzjb25mawc.net. I'm sure that's a host somewhere. And my transaction ID is FFDF. So this is going to be a note to Bob. Now, first of all, one of the signatures that would catch this right away, just so you guys know, if Bob's not a DNS server or shouldn't be getting DNS queries, that's going to be a gotcha, right? So this is just for an example, so you guys can see Scapy in action. But you want to understand the behavior of your source and endpoints, right? You want to understand, well, what is Bob doing? Is it a workstation? Is it a DNS? You know, should it be resolving DNS, getting DNS requests? So that's something to keep in mind when you're designing these. So now Bob replies. He's received the DNS command and has created an encoded string, and you can see that's kind of a messy looking in Wireshark, but it's requesting get /index.php, and it's sending the variable AC in the request URI. And then Eve decodes. So Eve receives the IF config results, decodes that from the response in the HTTP packet, and spits that out to the terminal. So this is really, really basic code, as I said. I would challenge everyone to download a copy of this, get familiar with Scapy, try this out. You can set it up on the same host. You don't have to have two different hosts. See if you can modify the functionality to make this a little bit stealthier in the environment. What we really want to do at this point, though, is use the best carrier protocol, right? So we just saw a basic command and control setup with Scapy and Python, but we want to understand what's running in the environment so we can find something that's a little less likely to be caught. Sending DNS to workstations is not a good idea. Sending HTTP GET requests at 2 a.m. from Bob's workstation is also not a good idea. So these will likely be identified. You want to analyze the traffic in the environment. There's a lot of ways to do this. I don't recommend installing Wireshark on a compromised host. That will probably be caught. Yeah, so that you probably don't want to do that. Furthermore, you may not have access to something like TCP dump, but luckily Scapy comes to the rescue again. We can implement some really basic code to analyze the environment because of the sniff functionality. So we can sniff traffic. There's a quick and dirty script on the GitHub repository to sniff traffic, identify the layers in the environment so that you can see what traffic is occurring most often and sort it in that fashion. You may also, you can extend this functionality. Let's say you want to target the traffic that's going to specific hosts or from specific hosts. It's very easy to build code that will provide that. So you can really start to baseline your network environment and identify the best carrier. So the command, I'm not going to go through all of the functionality here, but as you can see at the top, I used this on 300 packets, so I captured 300 Ethernet, 209 UDP, 137 RAW. RAW is the indication that Scapy has no way of decoding and identifying the information. So you might see RAW if you see a TCP packet with some strange unknown protocol, or one of those weird little proprietary protocols that vendors like to develop and put out there. And then we have things like IPv6, ARP, padding layers in the protocols, IP, DNS, question record. So you can start to see what the network is providing in terms of a transmission medium. This is where we get to have a lot of fun looking at network protocols. And there's two ways that I usually do this. Wikipedia is a really great source. You can Google too, but Wikipedia almost always has a really excellent article. In fact, OX8899, the Realtek Remote Control Protocol, there's an article on that. So you can usually find information about the protocols in the environment in Wikipedia and get some really good, community developed, human readable stuff. Alternatively, you can go to the IETF and read the RFC for the protocol. Oh, that is really small, but it's some beautiful ASCII art of the exact same picture I just showed you. This is from the RFC for Transmission Control Protocol, the original one, and this is the state diagram. I have actually printed up RFCs and read them, parts of them, but it's pretty bulky. So I recommend that if you're going to identify the protocols in the working environment, just go to Wikipedia, look on Google. You may also find information. So for instance, when I was looking up SSDP, I got to read all the nice articles around 2014 on the denial of service attacks that became very popular using SSDP right around that time. So you may find some added information that might help you make a better decision, a more informed decision when you read up on the protocol. So don't rely just on your packet captures or even the Scapy build. Okay, so SSDP is going to give us, first of all, a little bit more space in the environment. So this is really helpful because let's say I want to build a channel where I'm going to exfiltrate some data and I'm really excited and I'm like, oh, cool, there's this reserved flag. Awesome. So I get 1 bit for every packet I send out, right? So you need to identify a protocol that's not only going to provide you with the covert level that you need, that's going to match the environment, but also the transmission rate is a big deal. Unless you've got infinite time and you don't really care about exfiltrating, in which case I have no idea why you're even worried about this. So you want to identify a protocol that's going to give you a mechanism to put less easily signatured data in, less easily analyzed information, and you can start by targeting information that you see a lot of, again, vendor-centric, the more obscure protocols, or the more dynamic protocols. So this is a text-based protocol, HTTP over UDP, pretty useful because if you look in an average environment where there's more than one device sending out SSDP, you're going to notice that they all do it a little bit different, and it's very heavily text-based. When I see a heavily text-based protocol, I think, look at all those bits. I have so many bits there to use. So this is going to be a useful one, particularly if the network administrator wasn't thinking about something like SSDP when they developed the environment that they're working in. So Scapy provides a lot of ways of doing this. So as I mentioned, a raw layer, this is a really easy, quick way of throwing this together. I know what the protocol looks like. I'm just going to construct it by strings, piece by piece. So I'm going to create a variable, SSDP, and I know what the SSDP looks like, so I'm just going to put it together step by step, and then create a packet. So I'm sending an IP packet. This is a multicast protocol, so that's why you'll see a lot of SSDP on a network going everywhere. That's kind of convenient, right? Because someone's going to say, oh, it's a multicast protocol. Of course it's going to be going to Bob. Why not? I think. So we've got the multicast IP address. We've got UDP. It is a UDP 1900 protocol. And then we're throwing in, that should say SSDP without the parentheses. And that'll actually send out the SSDP packet constructed as a raw component. It'll look right on the network. If you sniff it with Wireshark, you'll actually see that it picks it up as an SSDP packet. But you're not really going to be able to do a lot of transactions within Scapy for it. You can create a cleaner constructed custom layer, and this is where Scapy gets really cool. So you can actually create a class with the packets that you want to use. So here I'm doing almost the same thing. I'm really basically building out the fields in an SSDP packet, and this is just a concatenated version. This is the minimum header that you would need for a packet sniffer to pick this up as SSDP. So I've got the fields, and I'm just using string fields for request method. I'm even adding spaces in manually. This is very simple. And that will also get picked up as SSDP. And here's that exact packet thrown onto the network. And you can see that we've got a lot of space left to add the typical string values that we would in SSDP. Okay, I'm actually running out of time, so I'm going to wrap this up. So the exfil.py, and I didn't have a copy of the code in the slides, but that shows the basics on construction. The next topic you'd want to dig into, you can build not only packets, but you can actually build custom fields and manipulate the fields as you need to based on the format of the field. So Scapy has very extensive documentation. I'd only be repeating myself to throw it in the slides, but you can actually construct any amount of packet architecture. And you can also identify things like default behavior. So I mentioned DNS automatically assumes UDP port 53. You can bind the layers and identify default behaviors within Scapy as well. So you can build a very full-featured extension to the Scapy library. The last piece, as I mentioned, I'm doing another workshop today on the ESP8266. You can use them for Subversive IoT. There are a lot of other platforms. This is the one I'm doing in the workshop because it's easy to use and really cheap. But Raspberry Pi 0W, I'm really excited to dig into some of those after Anycon because I've got a new project with those. Arduino, Teensy. We've actually got a discussion on Teensy in penetration testing in the Hacking Village in a little bit. Okay, I've got 5 minutes left, so any questions? I just flew through that a lot. There's a lot of talking and a lot of Python verbiage. If you guys have any questions later, come up to the village and feel free to check out all the gear. The ESP8266 workshop was a little more popular than we expected, so you may or may not be able to get a kit. But if you don't, let me know. I will get you a copy of the handout, and I will show you the parts on Amazon. It is seriously about $20. It's very cheap, very easy, and the handout will walk you through the whole thing if you want to try it out. All right, thank you guys.